All right, we are taking a look at the second part of our gas laws, which is Dalton's law of partial pressure. So when we say partial pressure, the partial pressure of a gas is the pressure exerted by one gas in a mixture of gases. Okay, so if we have a mixture of gases, multiple things all mixed together, when we say partial pressure, we're just focusing in on the pressure of one of those gases. So Dalton's law states that the total pressure of a mixture of gases is equal to the sum of those partial pressures. So let's take a look at this picture to give us an example. So we've got, let's say that this gas in the first container is hydrogen and the second container is oxygen. So we would say that this container with hydrogen, whatever its pressure is the partial pressure of hydrogen. In the oxygen container, it would be the partial pressure of oxygen. Okay, so each of those have their individual pressures. If we combine them into the same tank with the same volume, then we could take those pressures and simply add them together to find our P total, our total pressure. Okay. So each of the pressures of the hydrogen and oxygen, we can add together to find our total. And we can do that this is the official equation for Dalton's law, and we can find the total pressure from as many pressures as we have in a mixture. So these little 1s, 2s, 3s just represent the pressure of that specific gas, so we can replace it with the label for that gas to help us out. So let's look at an example of an application of this. A scuba tank contains a mixture of O2 gas at 0.65 atmospheres and helium gas at 0.38 atmospheres. What is the total pressure? So if we wanted to write just an equation for this, of what it would look like, our total pressure would be the pressure of oxygen plus the partial pressure of helium. So we could plug into that equation. O2 has a pressure of 0.65 atmospheres. Plus helium is 0.38 atmospheres. Notice the units are the same, so we can add these together. If they were different units, we need to convert one of them to make them match. So our total pressure would be 1.03 atmospheres. All right, so we can simply add them together to get a total. So that's one application of Dalton's law of partial pressure. A second application is more of a lab application. So it says gases are often collected over water to ensure all of the gas produced from the reaction or the situation is collected properly. Okay, so let's take a look at this setup. So we have a reaction producing gas. So let's say we're reacting baking soda and vinegar, and we're going to produce some carbon dioxide gas. Well, this is a sealed container with a tube. So these bubbles will come up and they're going to start traveling through the tube. So we've got carbon dioxide going through the tube. And then it leads to another container which is filled with water, and then a test tube. You would take this test tube, fill it completely with water, and then turn it upside down and place it in the container. Then feed your tube underneath the test tube so that we could bubble the gas through it and then collect the gas here. So we've got our little carbon dioxide bubbles coming up and we're collecting them. Now, the key here is in this test tube, if we can make it bigger, okay, so we've got the water below. We're collecting our little carbon dioxide gas bubbles. I'll just use a circle for carbon dioxide now. The other thing that's going to happen is we're going to actually create a mixture of gases because our water is going to evaporate. Depending on the temperature it's at, it will evaporate, and different amounts will evaporate depending on the temperature. So we're going to also have some little water molecules. Let's just use some filled in dots for water. So this is no longer a pure gas, it is a mixture. So this creates a mixture of gases. One is water vapor plus our collected gas. So whatever gas our reaction is producing that we wanted to collect. So all of that is getting collected in this collection tube. So if we want to figure out our pressure of our collected gas, in this case our carbon dioxide, we have to deal with the vapor pressure, which is, when we say vapor pressure, we're talking about the pressure of water, and it is determined by the temperature of the water. Okay, the higher the temperature of the water in the experiment, the more vapor pressure we're going to have, the more water is going to evaporate. So vapor pressure, when we say that, is the pressure exerted on the container by water. So to determine the pressure of the collected gas, so in this case our carbon dioxide, the vapor pressure, or the pressure of water, must be subtracted from the total pressure. Okay, because we're looking for the carbon dioxide, one of the partial pressures. We have one of the other gases, and we would have the total pressure. So it looks something like this. We know our total is equal to each of the individual gases added together. So if I wanted to find my carbon dioxide, it would be equal, if I wanted to find my carbon dioxide, I would need to subtract my water from my total pressure. So minus my pressure of water would give us our pressure of carbon dioxide. So that's how we could think about this, right? Whatever our total pressure is, we're going to have to subtract out that water to find our gas we're collecting. So anytime we're dealing with collecting a gas over water, this is how we'll rearrange this equation. So let's take a look at another example. So it says a sample of nitrogen gas, N2. Remember, nitrogen is one of our diatomic elements, so we write it as N2. It's collected over water at 20 degrees Celsius and has a pressure of 772.0 torr. So the container, or the total pressure, is 772. What is the pressure of the dry gas? Now this is an interesting term that's used. When we have the gas collected with the water, we call that a wet gas because it has water with it. So if we want the pressure of the dry gas, we want the pressure of the nitrogen all by itself. We want to take away the pressure of the water. So again, we want to take that total pressure, equals, we want to subtract the pressure of our water, and that will give us our pressure of our dry gas, in this case nitrogen. So our total pressure is 772.0 torr minus, now this says vapor pressure of water at 20 degrees Celsius. So remember, it's temperature dependent, but we're not plugging the temperature into this equation. It's just saying, hey, the water is at 20 degrees Celsius. Here's what the vapor pressure is at 20 degrees Celsius, right? Because it'll change depending on temperature. So 17.5 torr is the pressure created by that water. Again, our units match, so we can subtract them. And what we get is 754.5 torr. In terms of sig figs, remember we're subtracting, so we want to keep the number of decimal places consistent. In this case, we have 1, so we have 1 in our answer. Up here, when we added them, we had 2 decimal places, so we kept 2 in our answer. So that's another application of Dalton's law of partial pressure. If you wanted to, you could pause here for a minute and try a couple of the Dalton's law practice problems and then come back, or you can keep going. Our next part is the mole fraction. So mole fraction, we have looked at before in this class. We're just looking at it with a different application, and we're going to use it a little bit more to relate it to pressure. So the mole fraction is a value that shows the fraction of moles of one gas in a mixture of gases. It has no units because they cancel out. So again, this is mole fraction. We've seen this before. That large X is the symbol for mole fraction. We've got moles of a chemical over the total moles. So the A is just representing an individual chemical that we're specifying, just like the numbers did on the previous page. So let's just look at an example of calculating mole fraction. So it says find the mole fraction of argon and krypton in the following gas mixture. So those would be separate questions, separate equations. So let's start with our mole fraction of argon. We want the moles of argon divided by the total moles. So 2.5 moles of argon over our total. Now I'm just going to find our total over here in our mixture. We've got 0, 0, 1, and 5, 6, 7, 8, 9. So we've got 9 moles total. So 2.5 divided by 9, we end up with 0.278. We do want to go ahead and calculate that answer and find a decimal value, even though it's called mole fraction. But this kind of tells us, like, hey, this mixture of gas is about 27% argon. Okay, we could kind of think of it, a mole fraction is kind of like a percentage. We're just not making it into a percentage. We leave it as is. So if we did krypton, it has 5 moles of gas, of krypton gas in the mixture. The total is still the same, so your denominator stays the same. Notice that your units are going to cancel. That's why we get no units. And our krypton is 0.556 for its mole fraction. So about 55% is krypton. Now notice that our amount of argon versus krypton is twice as much. So there's twice as much krypton as there is argon. Well, that means that the mole fraction is twice as much. Okay, so there's twice as many moles of krypton as there is argon. Helium would be a smaller amount because we don't have as much helium in our mixture. Well, why do we care about mole fraction when we're talking about gases? Number one, it can kind of give us an idea of the makeup of the gas, okay? Especially if we didn't have these values, we just had the mole fractions, we'd kind of be able to tell, like, oh, there's more krypton in this than the others. The other thing we can do is relate it to pressure, and this is a very powerful equation that we can use. So the mole fraction of a gas can be used to find the partial pressure of a gas in a mixture. Multiplying the mole fraction by total pressure gives the partial pressure of the gas. So let's think about this. If we had a container, 2 gases, and okay, there's my 2 gases. If these open circles, I have more of those than I do my filled in circles. So when those particles are flying around, they're hitting the sides of the container. And because there's more of them, they are going to hit the sides of the container more often, creating more pressure. So whatever fraction of this mixture is those open circles, it's going to have that same fraction of the total pressure. So if 60% of the particles are these open circles, then 60% of the pressure is going to come from those open circles. So this is how we can combine the idea of mole fraction with our pressure. So we can see this equation. If we have the total pressure, we can multiply by a mole fraction and find our pressure of the individual gas. So let's just try one with our argon here. So if, let's just say, so we're going to go up here. If, the total pressure of this mixture over here is equal to 3.5 atmospheres, okay? If I wanted to find the pressure of argon, then I would take the total pressure, 3.5 atmospheres, and I'm going to multiply it by my mole fraction. When I do that, I'm going to get 0.973. My units don't cancel, so I get atmospheres, which is a pressure unit. So what this is saying is if 27%-ish of my mixture is argon, then 27% of the total pressure comes from argon, which is 0.973 atmospheres. If I did the same thing for krypton, 3.5 times my mole fraction, we end up with 1.95 atmospheres. Notice it's about twice as much, right? If the mole fraction is twice as much, if I have twice as many moles of krypton, then I'm going to create twice as much pressure from krypton because there's more particles there. They're bumping into the sides of the container more. So that's how our mole fraction and our partial pressure, total pressure, can be used with each other. So let's look at this example. What is the partial pressure of helium? So pressure of helium in a mixture of gases with a total pressure of 6.20 when its mole fraction is 1.5 or 1.25. So the mole fraction of helium is 1.25. So we've got all three of these pieces. We're looking for a partial pressure. We have a total and a mole fraction already calculated. So the pressure of helium equals our total pressure times our mole fraction. So if we multiply those, we get 0.775 atmospheres of pressure. So if, let's see, in this one, our helium is about 12.5% of the mixture, right? That's its mole fraction. So this is about 12.5% of the pressure in the mixture created by the helium. All right, let's look at another example. It says, what is the mole fraction of oxygen? So we're looking for the mole fraction this time in a gas mixture if its partial pressure is 0.35 atmospheres. So we have our pressure of oxygen, and the total pressure is 2.7, so we have P total. So similar makeup, we've got these same three pieces, total, mole fraction, partial pressure, but we're looking for the mole fraction this time. We're looking for a different piece. So let's just set it up and rearrange it. We've got our pressure of oxygen would be our total pressure times our mole fraction of oxygen. We want to solve for this mole fraction, so I'm going to divide by my total pressure. So let's look at that and think about it. Our mole fraction, if we had moles of things, we would do moles over total moles and get our mole fraction. But we don't have moles in this case. We have pressures. Well, let's look at how it rearranges. Pressure of oxygen over the total pressure. It's essentially the same equation, just different units, right? We're just looking at the ratio of our pressure of oxygen to the total pressure. So we can basically create a mole fraction or a pressure fraction, and they're going to be the same value. So our pressure of O2 is 0.35 atmospheres, and our total pressure is 2.7 atmospheres. So our mole fraction of oxygen is going to be 0, let's see, your units do cancel. So that's good. Our mole fraction doesn't have units, and we get 0.13. I've got two significant figures here. So this is saying, hey, 13% of this mixture is oxygen because 13% of the pressure comes from oxygen. Well, that's pretty straightforward, right? So we can set up a fraction using the pressures or using moles. We have options now. Let's take a look at one more question here. It says a gas mixture at STP contains 0.15 moles of helium, 0.24 moles of neon, 0.46 moles of argon. So we're given moles of each chemical. What is the partial pressure of neon? Okay, well, we do have this STP part. So this mixture is at STP, which means our total pressure is equal to our standard pressure. Our standard pressure is 1 atmosphere. Something we need to remember, right? STP gives us a value. It's not giving it straight up. We have to think about it. But it is on our equation sheet. So we have a total pressure. Let's look at our equations. We have a total pressure. We want a partial pressure. And we have moles. We don't quite have a mole fraction, but we could replace this with the moles of our chemicals and calculate that mole fraction. It's the same thing, right? So we'll do it all as one step. So our pressure of neon equals our total pressure times our mole fraction. Well, we're looking at neon, so we want the moles of neon over our total moles. If we add all these together, we end up with 0.85 moles. Those units will cancel, and we're left with atmospheres, which is good because we want pressure. So if we calculate this, we have 0.28 atmospheres, ATM, of pressure. All right, so about 28% of the pressure, or excuse me, 0.28 atmospheres of pressure comes from the neon. All right, so those are different ways we can use those equations. We can, this is the one that I see students forget a lot, is that they're given pressures, but forget that you can find mole fraction from pressure, so keep that in mind. Up here, these different forms of the equation, all I did was replace x with what it represents, that mole fraction. And then over here, I just rearranged it and divided by my p total, so you could see that the mole fraction, that ratio, is the same as the pressure fraction. So we can use it either way. These are interchangeable, right? They both are the same as our mole fraction. So you've got some practice on this. Try these out and let me know what questions you have. Thanks.